In this module, we will be introducing ourselves to the concept of the derivative of a function. So again, just to remind you, by function, we mean something f of x defined from a domain D to a range R, where this x takes value from anywhere in this domain. So the derivative of a function, its notation is typically f prime of x. So you see a little apostrophe up here, or df by dx. These are two common notations used for the derivative of a function. As we go into multivariable calculus, you will see how this df by dx changes into some other things. But for now, in single variable calculus, these are the two notations. So let's try to understand what these things are all about. So let's start with a very basic intuitive example, which actually goes back to the concept of a slope of a function or the slope of any curve. So let's say our function here is the temperature in Maryland, in Washington, DC, as a function of time. So here we have time, and here we have temperature, and we measure time in the unit of months. So let's start at, and I don't care about the full 12 months, I'm just gonna focus on the summer months, or let's say spring to summer. So we have March, April, May, June, July. I ran a bit short here, let's extend this. August, September, October. So this is our time curve. And so instead of x, we have time, and and the function here is the temperature at that given time. So how would it look like? Roughly, it would look like, as in March, it's very nice and pleasant. April becomes a bit warmer, May becomes a bit warmer, June becomes a bit warmer, and July is even higher, August is even higher, September it starts to fall down, October it falls down, and then it keeps going down, right? This is a typical profile, no claim to accuracy over here, but this kind of captures the behavior. And you see I have made it a bit jagged because it fluctuates day to day. So this is our temperature over profile. Maybe it peaks in August. So what I need you to think about is this notion of the slope of a function, which basically captures the rise by run. For a given amount of time change, let's say we went from May to July. In 2 months, how much did the temperature change by? So it changed by some unit. So let's say this is a change of 10 Fahrenheit in 2 months. So the slope over May to July would be given by 10 Fahrenheit by 2 months, or 5 Fahrenheit over month, right? This is the slope. And you can define such a slope for any generic function. If you went instead and looked at the slope from September to October, and you went from here to here, September to October, the same slope will be negative because the temperature is on an average decreasing. So from September to October, this slope will be something like approximately -5 Fahrenheit per month. And that tells you that the function is on an average decreasing. And we don't have to do it just over 2 months. We could have done it over a period of 1 month. We could have done it over a period of 1 week, period of 1 day. And that exactly is the idea behind the derivative. The derivative of a function, of a generic function, is defined as the limit of that function. So we are talking about f prime at a certain value of x. So we take, if you recall last time we talked about the limit, which is the limiting value. So here we take the limit of that function at some value x plus delta x. So actually, let's go to the next page, because this is such an important concept on which everything in the future modules will be based upon. So let's draw a function, some generic function, which looks like x, f of x, and it's some function which does something. So let's say we have a particular value of x, and let's say we have a value of x slightly changed, x plus delta x. So in this regime, let's say the f changed by a value of delta f, right? From here to here, that is the increment that you observed in f. So given this, we define the derivative. It is very similar to the slope that we calculated for the temperature versus time profile. We just make it sound a bit abstract now. And so here it's defined as f prime of x. Again, the same notation, same thing as writing it as df by dx is given by the limit of f at x plus delta x, which is this value over here, and f at x, which is this left value, the difference of these two, divided by the change that you caused. So this is the same as the rise by run we saw in the last page. And we take this limit as delta x tends to 0. So this is the rigorous definition of the derivative of a function. And as you can see, the x has to become very small for this to be correct. We can go one step further. We can calculate not just the derivative of f of x, we can calculate the derivative of f prime of x. So this is pronounced as f prime of x, or f dash of x. You will see people using different names. We can also calculate what is called the double derivative. So this was the single derivative, and we can also calculate the double derivative, which will be given by d of f prime by dx. It's also called, so if you put in the value of f prime over here, that becomes d by dx of df by dx, and the common notation that is used for it is d squared f by dx squared. So notice this peculiarity that the power in the numerator goes on the top of d, while the power on the denominator goes on the top of x. So in this case, if you calculated the slope at every different derivative at every different point, that is a function itself, right? That is an operation of a function, just like we saw the quotient and things like that. You could go back and calculate the derivative of that derivative itself. You could go and do higher order derivatives. You could do a third order derivative. So this double derivative could have been called double order or double derivative. So when it just says derivative, it means a single derivative. This would be given by f triple prime of x is equal to d f double prime of x by dx is equal to d cube f by dx cube. We are going to stop this module here, and next module we are going to study and calculate this for lots of examples so you gain comfort with this. I will leave you with a problem to think about. If f of x is the exponential, can you calculate the 44th order derivative of f of x? What will it be? I want you to think about this before opening the next module. And if you get it right in the next module, you should give a prize to yourself. With that, thank you very much.